Hello, everyone, and welcome to episode 1 of the Asclepius podcast, where we talk all things medicine and science with your host, Timothy Ju. Now, I kid you not, I am currently in my car, in the garage. It is cold, it is Colorado, I'm wearing my shorts, I'm in a hoodie. So let me just explain the context. Essentially, my grandmother loves to live in 80-degree weather. The house is screaming, there was no quiet place left, so I decided to go here. With that out of the way, let's talk about this podcast. So today we have Dr. Karolin Luger. Now, after a much-deserved lengthy introduction, we will listen to a class project from yours truly singing about the amazingness of the liver, and then we'll start talking about things ranging from cryogenic electron microscopy, pursuing learning for learning's sake, personal care, and so much more. Please don't forget to like, comment, rate, subscribe, share, and all that good stuff. It really helps the algorithm and will get the information out quicker. Regardless, hope you all enjoy. Oh, hi there. So before we start today's episode, let's go over our sponsor, us. Now, if you are dying to part with your hard-earned cash, then feel free to support us on patreon.com/the Asclepius podcast. That's TheAsclepius podcast. Perks include being able to ask questions to future guests, suggesting future guests, getting cool original merchandise, and so much more. Hopefully, this is the first season, so we don't know how it's all going to play out, but either way. Then once again, visit our patreon.com/the Asclepius podcast, or visit us at asclepiuspodcast.wixsite.com/home. Eventually, we'll try to get our own domain too. Anyway, look forward to seeing you soon. Are you extremely gifted? Do you have complete mastery over the arts? Well, my friends, if you are literally Leonardo da Vinci, DiCaprio, reincarnated, I would highly encourage you to participate in the seasonal Asclepius Podcast Art Challenge, where we have but the most able of artistic maestros submit their rendition of the Rod of Asclepius. Those that happen to edge out their competition will have their art not only used as our logo for the season, but will also have their art used as merchandise, with all the proceeds of that merchandise donated to Children's Hospital. How altruistic of you. If you are interested in showcasing your amazing talents or just helping out Children's Hospital or the podcast, then feel free to submit your art at our website at asclepiuspodcast.wixsite.com/home. Anyway, let's get back to the episode. So, for today's guest, we have Dr. Karolin Luger, a biochemist, biophysicist. Not only is she an amazing scientist, researcher, professor, and mentor, but also a pretty cool person. She did some stuff in her career, such as discovering the structure of the nucleosome through X-ray crystallography. Now, this was not only one of the most difficult crystallography problems at the time, but also one of the most influential. She's also the only person in Colorado to have been named a Howard Hughes Medical Institute investigator. Now, Dr. Luger is continuing her research at CU Boulder, and with no doubt just as much passion as she had when discovering the structure of chromatin, or with the passion with which she inspires future generations of scientists as a professor. A little more cool tidbits: she has her own Wikipedia page, a really cool Twitter account, and her image of the nucleosome is like everywhere. Feel free to just search up nucleosome X-ray crystallography on Google Images and just thank me later. So pretty. In general, if I had to sum up Dr. Karolin Luger from our brief interactions, I would just think of the stereotypical mad scientist, add some groovy dance moves, an obsession with the liver, constant references to watching Game of Thrones, a cool Austrian accent, humility, a wicked drive, and a strong sense of character. Fun fact, while I was first developing the podcast, I sent an email to Professor Luger, and despite her busy schedule, she emailed me back within the hour saying yes. We just got Professor Karolin Luger. Oh, what? Yo! I was stoked, to say the least. So, with a lengthy introduction of Dr. Karolin Luger out of the way, Dr. Karolin Luger, if you don't mind, how would you like to introduce yourself?
I'm a structural biologist at CU Boulder, and I'm also a teacher. I teach undergraduates like yourselves. And I also train the next generation of scientists, grad students, undergrads, high school students, everybody milling around in the lab. That was before COVID. Now it's less milling and less density. But I'm just a super curious person, and I'm a nerd like most of you. I own it. I'm just really interested in finding out how stuff works. And I also like playing with shiny, expensive toys and instrumentation. And so this job is perfect for me.
Being a nerd is totally cool, by the way.
Perfect. That was such a better introduction than I could have done. So, Professor Luger, before I start asking you like the legitimate questions, I did have to ask you this. I was just wondering, out of all your art projects that you've seen from students, which one was the coolest? I want to see if you could out any students.
Well, I'd have to out you and Maddie, because I'm a huge Passenger fan, and that song was just amazing. It was kind of in that style. And it is actually the example I used for my current class, the Selfless Liver, one of my top all-time favorites.
This is the song that Maddie and I turned in for our project, and it ends at 5:54 if you'd like to skip. The song does not end at 5:54, by the way.
Selfless liver, selfless liver, so leave your liver alone. What are you thinking with your underage drinking? You shouldn't really play with homeostasis, so you need to regulate the nutrients you ate 8:30. Otherwise you're bad. Don't take one more shot of whiskey, cause it's risky. Can't say why, but it gets tricky. May not always be the case, but it has G6 phosphatase. Ooh, ooh. Your liver has G6 phosphatase. Transports glucose to your brain and muscles. Don't worry if you're starving, cause it all converts fats into ketones. You sorta need those, that's gonna help you fit into those clothes. So take care of your selfless liver, selfless liver. Watching Game of Thrones, selfless liver, selfless liver. So leave your liver alone. Selfless liver, selfless liver. Watching Game of Thrones. Selfless liver, selfless liver. So leave your liver alone.
Flailing around the amp. Flailing around the amp.
HDL receptors, don't neglect your, but respect your lovely liver. Lovely liver, oh. Best of all, it regulates cholesterol. If you're abusing your liver, you probably eat takeout dinner and all that high-fat food that you improperly chew is going down your tube and coming out as a big woo. Selfless liver, selfless liver. Watching Game of Thrones. Selfless liver, selfless liver. So leave your liver alone. Selfless liver, selfless liver. Watching Game of Thrones. Selfless liver, selfless liver. So leave your liver alone.
Flailing around the amp. Flailing around the amp.
Selfless liver, selfless liver. So leave your liver alone. We did it! Yeah. Woo!
Overall, fabulous. It's super hot.
So to set context for everyone who might be a little confused, when you take a class with Professor Luger on metabolic pathways, one thing that becomes very apparent is Professor Luger's love of the liver. She adores the liver very much. And I think Professor Luger liked it because she posted it on her Twitter.
It was beautiful, and you should actually post it with this podcast so that more people enjoy
I
it.
should probably do
With
that.
Maddie's permission.
I mean, I'll rest easy.
It is just
Yeah.
part, and I just will say about the liver does everything in our bodies, and we should do a whole podcast about the liver. And this is really not my area of research, but the liver is flipping amazing. So,
And yes, the liver is super cool. Now, although the heart and brain are my personal favorite organs, the liver is definitely a runner-up. The liver is an absolute unit when it comes to metabolic activities, almost acting as the central hub. So let's do a quick rundown on the liver. Humor me. Obviously, one of the main motifs of metabolism and biology in general is maintaining homeostasis, to maintain balance, just like my homeboy Le Chatelier. So, of course, there's these little pockets of defied entropy, but in general, the overall system ends up finding its way. Now, when we're a little imbalanced, the liver sure does its part to get us back on track. For instance, if we have too much fat in our blood, the liver will be integral in breaking down those fats for energy. It also produces this thing called bile, which really helps emulsify or isolate fats within the duodenum of the small intestine to be broken down and played with later. But wait, that's just one macromolecule. We also have sugars and amino acids, which the liver also helps us with. For sugars, if we have hyperglycemia or a high sugar concentration within the blood, the liver is just going to start building up glycogen, a form of sugar storage, and whenever we need that sugar, it's going to start breaking down glycogen for us. As far as amino acids go, the liver can utilize these building blocks to create fats or sugars as needed, which unfortunately produces a harmful byproduct of ammonia, but no need to worry, because the liver already got us covered. The liver will route that ammonia in the form of urea to the renal system, where we can then pee out all of that nastiness. You know you're in good hands. Also, unlike the brain and heart, the liver has mad regenerative properties, so feel free to drink away. Except don't, like I said, always consult your personal physician before you decide to listen to a random biochem graduate that has too much time on their hands and is still waiting to get into medical school.
One thing that I wanted to ask you about was, I remember roughly around like after my second midterm, I went on Google and I just searched up metabolic pathways. And I got really humbled because I saw a document where there's just like, it looks like a page heavy with ink compared to like us undergraduates. How much more of that sheet do you know compared to us?
oh my God, I'm gonna let you in on a secret. So the first year I taught this class, I knew about as much as you did before you took this class. I had taken it 30 years ago, and that was kind of whatever I could dredge up from my memory. I had a very stout German-speaking professor. And so I remembered a couple of things, him saying in his very stern German voice, all these difficult compounds. But I really didn't I had an overall understanding, but a lot of the detail I didn't know. So I really had to dive into the material and not only understand it, which wasn't that hard because it's pretty straightforward material, but to make it so that I could convey it to you in an intelligible way. And so teaching requires a different level of understanding as just learning the material, as you'll find out when you are a TA. But it was a really hard class to get started. But I really warmed up to the material. I think it's just so fundamental, and there's so many recurring themes, and just the overall beauty, how everything fits together and how everything kind of interdigitates is just amazing. And I'm in total awe of this material, even though it has nothing to do with anything that I research. And I think that's kind of a misconcept that a lot of students have when they are at any university. They think, oh, the professor just waltzes in and they teach about the stuff they know and then they're out of there. But
Right.
that is actually very, very rarely the case. And usually we teach stuff that we really know very little about. And it makes it challenging, but also rewarding because I learned a lot, just like hopefully you guys did. So, and I got some cool songs to listen to as well.
Can we just take a moment to recognize how cool this is? Like, how dope is it when teachers encourage you to learn from leading by example? I don't know why, but interacting with people who are so eager to take every chance as a learning opportunity just makes me feel all warm inside. Or perhaps that's a byproduct of the metabolic activity of my organs.
when you were in our shoes, do you have any favorite classes, any favorite moments where you were like, eventually this made me fall into the passion of research?
Yeah, I think, definitely my metabolism class, which really kind of sucked with them, but I did actually really like the material. And, it's kind of unfair because we stretched that whole material out over 2 years. So we could go into a lot more detail. But really where I started to become intrigued is when in high school, and we had a high school teacher in biology who he was an Aggie guy, and his passion was compost, but we had to teach us about translation. And at that time, the understanding was there, but it wasn't, of course, not at the detail that we have it now. But I remember he was talking about matching up the tRNAs with the correct amino acid. And this happens, as you hopefully know, in the tRNA synthetase. So there's some exquisite recognition going on.
So let's just go over the little story I tell my high school students about the central dogma of biology. We have the messenger RNA move into the ribosome home, which houses the reaction. When you move in, you better call your friends over for a little celebration, so you get the phone numbers or codons for your specific friends, the transfer RNAs. Now, those phone numbers are important because bringing over the wrong person can really mess up the whole party. Anyway, obviously, it'd be very rude to go celebrate your friend's new house without bringing any housewarming gifts, so these transfer RNAs bring their protein presence for building up phenotypic furniture. I know, what a set of alliterations. Now, in that process, we have these codons, right? The little phone numbers. Well, they're sort of supposed to call the right transfer RNA, which brings over the right proteins, but how does that really happen in the body? It's time to get granular. Well, essentially, we're going to have these things called amino acyl transfer RNA synthetases. What a mouthful. But don't worry, we're just going to call them gluers, okay? They glue things together, and they're really good at gluing the right parts together. After using the energy of ATP by hydrolysis, hydro referring to water and lysis referring to cut, the specific amino acid of choice, whether it be phenylalanine, tryptophan, tyrosine, whatever, that amino acid is basically going to get stuck on to the AMP, and we're going to have an amino acid AMP complex. We then just sprinkle in some transfer RNA with a specific codon. It sort of does the old switcheroo where we kick out the AMP for the transfer RNA, and then we are left with a recently dumped AMP floating around in aqueous solution, and our amino acid transfer RNA complex, or what we like to call charged transfer RNA, is ready to go in case it ever finds a buddy that recently moved in to a ribosome home. Hopefully that was some good review.
And I was really curious about them is because he didn't explain that at all. It's like he just said, oh, magically, the amino acid gets loaded onto the tRNA and then that's that. And so I asked him, and he was really hedging and waffling. And that's when I realized it's like, oh, wait a minute, like there's a lot of stuff that we actually don't know, because I think a big mistake that's being made in all teaching, definitely in my education, is that, you have a textbook and it's full of knowledge and that's it. And the book is closed. Mm-hmm. And the truth couldn't be further from this, because we are always recognizing new facts. We're discovering new pathways. CRISPR-Cas is the most recent example that's really fundamental. And so the book is not closed. And I think it is kind of disheartening for somebody like you to sit in class and think like, oh, like all these old German dudes already found everything. And so like, what am I doing in this area? So that's kind of what I wanted to convey to you guys. And that's also what keeps me going, because there's always new stuff to be discovered.
The book is not closed. What a cool thing. The lack of understanding is not what deters us, but what drives us to move forward. Beautiful. Also, Dr. Luger brings up another crazy topic: diversity and representation within fields of study. Now, this is such an important topic, and as much as I would like to get into this now, this will have to be explored in future episodes, so just sit tight, my beautiful listeners.
What would you say has been the most amazing advancement in technology that you've seen for STEM? And what would you say is the next one that you're looking really forward to?
So for sure, in recent years, the so-called resolution revolution in cryo-EM, and as you know, it was awarded the Nobel Prize for 3 people, I think 2 years ago. So that was really cryo-EM has been around for a long time, and it kind of was at the stage of potatology or blobology, we call it, where you could discern protein complexes at pretty low resolution, but you didn't really know at the atomic detail what was going on. And so advances in software, in instrumentation, that's a little too complicated to get into, really made like a quantum leap possible, that now we can just slap these tiny molecular machines under a microscope and we can see them in exquisite detail. That's just flipping amazing. What is now the next big thing that is in progress is what we call tomography. So you can actually do this in the cell, which is even more amazing. So what we do now currently, and what's pretty mainstream, and we are doing this at CU Boulder as well, is you take the single machines or entities or complexes or DNA fragments or whatever, and you purify them and you place them on a grid, and then you visualize them. And now you can actually do this in the cell. So you basically take a cell and you take a really thin, a really fancy pastrami slicer, and you slice very, very thin slices under liquid nitrogen, and then you lift that little lamella up and put it on a grid, and then you can actually look at your complex of interest in its natural context. And they've done this with chromatin, my favorite substrate, and they're making some pretty rapid advances. So pretty soon, I think we don't even have to purify things anymore. We can just say like, I'm interested in this particular complex in the cell, so let's just cut it open and take a look.
Pastrami. Anyway, let's address the cryogenic electron microscopy, lamellae, tomography, so many heavy words, so little time. But don't worry, I got us with word dissections. Cryogenic, we could just refer to that as cold. Electrons, I want us to think of little cannons or little bullets, and small scopy observation. If we've learned anything from history, it's that if you don't understand something, shoot it. So we shoot some electrons at the particle of interest, some bounce off and some go through some parts with more density than others, and it creates an image on a detector directly across our little electron cannon. Sweet. Now why do we make these suckers cold? I did some research, and in fact I would highly recommend Low Temperature Electron Microscopy by Dubuchet et al. For the interesting read, but from what I was able to parse, essentially there is no conclusive mechanism on how cryostabilization actually works, but there are some leading hypotheses. Of course, one would expect the colder temperature to just be better in general for specimen, because with less available energy around, we are less likely to undergo any chemical reactions, structural changes, and etc., which would result in a higher resolution image. But in general, it seems like the behavior of electron beams at low temperature has yet to be elucidated, a science problem that requires current and future scientists. So let's get to work, people. So we cool down our sample to increase the resolution and prevent contamination, and then we shoot the thing to get a better look at it. Now let's address tomography. So tomo refers to slice. Maybe you could think of like tomato, I don't know. And graphie refers to writing, so slice writing. The lamellae that Dr. Karolin Luger talked about is essentially a fancy word for a thin layer of a cell or whatever. Now, I believe that what was being referred to is electron tomography, where we have a sample and shoot it with electrons. But there's a twist. Instead of a static sample, we decide to rotate our sample, and then after a series of bleeps and boops, we get our 3D image from superimposed cross-sections. Very cool. Now, another common application where you might have heard of this is the CT scan or PET scan, and this allows us to map the human body and do a lot of stuff from the same principles. In general, the science summary that we have today is that we cool things to reduce variability, increase resolution, and we shoot things with X-rays or with electrons or with whatever to get a better look at it and understand it. Now, after Professor Luger talked about her cool insights on technology and the relationships with research, I decided to trip over my words and thoughts for several minutes, and thankfully, Professor Luger was very patient with me. And eventually I got to asking her about recovering from failure. To set context, when Dr. Luger was originally getting prepared to image and derive the diffraction pattern of the nucleosome, the team had spent a decent amount of time with preparatory work setting up the sample for a higher resolution, but they ended up getting a lower resolution instead. Ouch. So, here's Dr. Luger's insights on failure.
How do you recover from such a painful realization? And how do you immediately start thinking, okay, well, this is the next step?
Yeah, I mean, that's a really good question. And everybody goes through this. Like you said, it's 2 steps forward and 5 steps back. And then I really do think what makes a successful researcher is this ability to pick yourself up from a anti-success, from failure, right? And turn that into success. And I think that holds true, and that's known now for business people, entrepreneurs, people like Elon Musk. Stuff goes wrong, and rather than dwell on it and say, oh, dang it, like I'm such a failure and this went wrong and I'm not good for anything, you just like, oh, this went wrong, what can this tell us? And I think that is a really hard skill, is to disengage yourself from the failure and not say like, oh, this experiment failed, I'm such a failure. But no, the experiment failed, and it's trying to tell me something, because I do think there's a lot of information in failure. And in my endeavors, that was certainly the case, that I did learn from things that went wrong. The temptation is always like, okay, that didn't work, let's do it again, or let's try something different. But it takes a little more, shall we say, I don't even know what it is masochism, to take a look and say like, why did you go wrong, experiment? Tell me, what could I do to help you work?
Right.
And that's what I tell all my students and all my postdocs, and they all laugh at me, but I really do think that is super important. And also, in a way, so not taking it personally is really important. Not to say that it wasn't really hard. What really helps is having a good community, colleagues who you can talk to, say like, oh, this didn't work. And they say, don't worry, it'll work out. Or, you go and have a beer or whatever. So having a good community helps for sure. Having a PI or a boss who is understanding and says like, we know stuff goes wrong, and maybe those 3 steps back will be good for something. It will maybe show us a different approach, so that helps. But in a way, and that's going to sound really bad, but in a way, I think a lot of researchers are like gamblers, like these people in Las Vegas, these really sad people who stand there and they pull the lever and they say like, oh, next time it's going to work. Next time it's going to work.
It's like chasing this dream.
It's in a way that is true, but in a smart way, maybe pushing the lever a little differently every time or something like that.
Something that you actually have some control over, I guess.
Yeah, but I really do believe that experiments do not fail. Like, things happen, and they happen for a reason in your test tube or in your experiment. And if you don't understand why these things happen, then something in your original assumption was wrong. I'm also, and not to wax too poetically about it, I'm also a big believer in kind of stepping back a little. Sometimes, so I always view problems, scientific problems or personal problems for that matter, as like 3-dimensional. So you stand in front of them and you see like one side of them, and you're just kind of trying to see the pattern or crack this problem. If you step back a little, or maybe step to the left or to the right, you have a different viewpoint, and that helps you to solve it.
Just figuring out the pattern and the puzzle that researchers and just people in general have to figure out to get to the solution is so inspiring. Do you have any example of research that you did where you were like, I'm not gonna lie, this one was a pretty cool application or something like that?
Yeah, I mean, that was very early in my career. I was trying to express a protein, and the protein, like sometimes when you express proteins in bacteria, they just don't fold properly, and so they form these aggregates in the cell. And
Right.
so somebody told me, oh, you just like dissolve it in urea, and so it's completely denatured, and then you just slowly take the urea out and refold it. And I'm like, that sounds like it shouldn't work. And it worked. And I remember I was like, wow. I was just floored by that. So, that's a really little thing, but, it was kind of an early time. Those are the moments we live for. And then, there's just like, not to put too fine a point on it, but a lot of it is just drudgery and persistence and more drudgery and but just kind of staying with it and keeping your eye on the prize and just keeping an open mind. Again, what are your experiments trying to tell you? Maybe you're there to prove one particular hypothesis, but your experiment suggests otherwise. When do you kind of go and follow that route rather than your original route? That's often, those are difficult decisions.
When you went into research, were you ever intimidated by failure, or were you more interested in the pursuit, or how did that all go for you?
I think a lot of people who enter this field have the imposter syndrome, especially people who don't look like the typical old white male guy. That, especially when I grew up, that was like the epitome of a researcher. Researchers didn't look like me. They didn't look like you, for sure. So you go in there and you think like, oh, can I really do this? And
Right.
so a lot of the driving force is really going in and saying, yeah, I think I can. But it takes a while to arrive at that stage. And so I will say, I think a lot of people are driven by the fear of failure. Whether that's healthy or not is kind of remains to be seen. But it's not as enjoyable a driving force as just a pure curiosity, for sure. But I think people would be lying if they said like, oh no, I'm just like totally only driven by the curiosity and this is so fun and awesome. They're always, you don't put in these long hours in the lab if you weren't afraid this whole thing wouldn't go belly up. Because at the end of the day, if you're a grad student or a postdoc, there's kind of careers on the line, right? If you screw up everything, then that's not a very good proposition for your PhD, for example.
When you were going through your research with chromatin, did you realize how big these implications were, or were you like, hopefully it gets like some traction, or how was that pre-realization, I guess?
Yeah, so this was at the time when I entered the field, it was really not cool. Like everybody thought transcription was cool, polymerases, all the factors that bound to the polymerase, all the transcription factors, that was cool. And chromatin was just kind of something that was there and just like a dumb rock in the way of the polymerase. And also when I entered the field, I didn't realize that, because I was super naive or stupid or both. I just wanted to learn crystallography. I had planned after my PhD to go on a big trip with my husband, and so we bought a camper and we skied and hiked and kayaked through North America for a year. And so I needed a good paying job afterwards. And so Swiss postdocs were pretty good, and I really wanted to learn crystallography. So then my PI advisor said, like we have these nucleosomes and they diffract to like 10 angstrom. So you just kind of tweak it a little bit and then, they will diffract higher and then you can do some more interesting things. So I thought, yeah, that's sounds okay. And he didn't tell me, and I didn't know that this was one of the hardest crystallography problems that there was.
Right.
And so, I got into this very naively and ignorantly, and I pretty soon realized that this was a big old horrible mess and would be super difficult. And by that time, I was kind of not willing to let it go and give it up. It was, however, at that time when I started, not really going to be something that would be so exciting. To be honest. And but like halfway through, there were some seminal experiments done by other people that really showed that these structures have a very profound implication to everything, like the
Right.
the transcription regulation and DNA damage and all those kinds of things, which is kind of, now you say like, duh, of course they do, but at that time. So then the field realized that, and then it became quite a big race and a big push to get these structures done because people really wanted to understand it. And we had actually, we had the journals like Science and Nature call us, which was hilarious. Like, can we please pretty publish your paper? So that never happened again. But that was good. And so only about midway through did I realize certainly that this would be a pretty big deal. And so that ended well.
A cool lesson on not necessarily following fads, but sticking to your guns. I like it.
So I think, well, people have like a misconception about like crystallography. They think you just press a button and then you see your image. But you said in that video, that was the research that I chose. You said that you spent like a year slaving away and just punching in numbers and understanding the data and using these complex mathematical forms. So by the time you ended up with your image, it wasn't really like a click and done. It was like a slowly chipping away.
Well, at that time, the technology wasn't as advanced as it is now. And so, and I don't want to get in the weeds here, but it's almost like you have some shady image that's not very high resolution and it's not very defined, and you kind of look at it and you try to guess, well, maybe there's an alpha helix here, maybe there's a piece of DNA here. And as you're doing this and as you're putting these pieces in, the map itself becomes better and better. So it's like a bootstrapping experiment. And so it's not like you press a button and ta-da, there it is in all its glory. It kind of slowly emerged. And some aspects in the beginning were pretty iffy. And like, I sat for about a year, I sat in a dark room in front of the computer screen, dialing knobs to manually build atoms into my structure. Right. And my colleagues would come in occasionally and they would say like, oh, and I would like proudly show them, oh, look, I built like this piece of an alpha helix. It took me like 4 days to build that. And they would look at this like, oh, come on, you don't really believe that, do you? So it's like, because it was really, it's like trying to make up something behind a thick fog of uncertainty. Right. And so that's a pretty lonely proposition, obviously. And I remember at that time, I had known crystallographers before, and they were in the lab when I did a PhD in the lab downstairs, and they were like this bunch of unwashed, hairy guys, smelly, and I'm thinking like, yeah, that is just gross. And then but after a couple of months of doing this, it's like, this t-shirt's plenty good enough. Like nobody's gonna see me. So you turn into this cave dweller that's barely fit for human contact. And I tell my husband, oh, I'll be home like in an hour, and then you look at the watch, it's like, oh shoot, there's like 3 hours have passed, and so you better run home. So it's a pretty it's not nearly as hard right now with X-ray crystallography, but it can actually be still pretty challenging with cryo-EM. But the automated tools are much better now, and so there's less human input. Now, on the flip side, there's probably nobody in this world that knows this structure better than I do, because I literally am on a first name basis with every single atom in the structure. So,
right. How did you figure out and recognize the diffraction and the electron density? How are you able to say like that's part of an alpha helix? And I'm not assuming it's based off of intuition.
It is. It's a lot less precise science. And so just to get into the weeds a tiny bit, what you do nowadays is a method called molecular replacement. So this is kind kind of weedy, but you kind of think, oh, this structure looks, you have a suspicion this structure looks like this other structure that we already know. So you just kind of put it in, and then you can determine the so-called phase problem from that, because you can't focus X-rays. And so you have to determine the phase problem. I didn't have that luxury because there was nothing that looked like this at that time.
Right.
And so we used a method called heavy atom replacement. And so basically you put heavy atom in, and then you get kind of a shadow of phases. So you get a very rudimentary map. And so then there's certain numericals that tell you that maybe your phases are correct-ish. But then what you do is you display that electron density on your computer screen, and then you just like look for like this telltale helical repeat, or you look like for the phosphates of the DNA. So it's a very intuitive business, and again, it's like a puzzle. So like I remember I would spend like days trying to fit something into this density, and it just didn't look right, and I really wanted it to look right, but it just didn't. And so you just have to throw it all out and start start somewhere else, because that means your original assumption was wrong, and it turned out to be wrong. And then when you do that, it's like, oh yeah, that makes like so much more sense. So it takes a lot of backpedaling, like you mentioned, like the 5 steps forward and 15 back. There's a lot of that going on as well. It takes a lot of intuition also. So it's actually not quite as a precise a science as one might have believed, or certainly I believed. I was quite shocked to see how intuitive this process is.
And so after you get your structure, right? And I've seen the diagram plenty of times. It's like a very pretty image. Were you like sitting back and you were like, no, there's something wrong, or, oh, is it like, or were you just like, oh, I'm pretty sure this is it? Or what was going through your mind?
Well, this is, so like I said, it's not like you look back and then ta-da, there it is in all its amazingness. You kind of see it grow, and you have your little problem areas. So because it's a large structure, some areas, like for example, the famous histone tails, they're very wobbly, and so they're very hard to pin down in the structure. And so a lot of these still looked wrong. So and they still are wrong because we can't define them that well. But other areas, you look at them, and we know a lot about how proteins pack. You have like 2 aromatic residues kind of packing like so. That's got to be right. There's only one way. And you look at how the protein binds to the DNA backbone, fulfilling all the geometries that we know to be true, and it sits exactly so. So it's kind of a mix of things. Every structure and most people actually don't appreciate this, but every structure has good parts and not so good parts.
Right.
And most people just take everything as like the gospel, but as crystallographers or structural biologists, we know like there's certain landmark telltale signs to know when the people who built this were kind of fudging it a little bit.
Right.
Yeah.
Do you have a picture of chromatin in your house anywhere, or are you like, I've seen it enough?
I actually not. I don't have a picture, but I do have a welded metal sculpture that Brian Whelm, a scientist at University of Utah, made for me, and I'll send you a picture because it is flipping amazing. So it's like this big. It is. Big. I would say it's like at least a foot in diameter.
Wow.
And it is anatomically correct, and it's beautiful. They have the beautifully welded alpha helices and the DNA. It is a piece of art, and I decorated at Christmas and at Easter, and it stands in my house.
I guess another question is this. I guess we talked about the downsides of seeing that iffy data, and you're like, oh no. How did you recover from your success? Because after that big high, isn't it easy to rest on your laurels, I guess? So how did you just start biting down and being like, there's still so much you have to do?
So this is it's a really good question, and one I really haven't thought about a lot. But I will say, as you're asking this, when I determine the structure, it's kind of anticlimactic because there it is, and then now what? And everybody thinks it's awesome, and then there's some people who think like, oh, why did it take you so long? So I had to deal with that too because it took us a long time. But I pretty soon went on the job market, and you kind of have to. You can't rest on your laurels. At least I'm not the type. I pass a bar and then I lay it higher, and that's just me. And then higher and higher. That's just my nature. But when you are on the job market for a faculty position, you kind of have to develop your own research program that's independent of what you've done before. And so that was actually really fun because for the first time, because this structure that we did was very, very targeted. There was one end game, nothing else. We needed the structure, and everything was geared towards that. So it was really not a very creative process. So now I could actually say like, oh, like now we have this thing. Like, what do we do with it? And what else? Where else can we go? So it was almost like the door opened, and I could like walk out in the open, out of the prison of my dark room where I worked on the structure. So that was actually quite liberating, and I didn't really view it as. There was a little anticlimactic. You see the paper and then like, oh yeah, well, that's what it was all about. But moving forward was really very exciting, and just seeing as I was interviewing for jobs, seeing how excited people were about the structure, because you get a little blasé about it, like I've seen it for so long, like what's so special about it? I actually remember I went on a job interview to Chicago, and it's like a 10-hour flight to Chicago and from Europe. And I spent the whole plane flight basically almost like memorizing and reminding myself what every single amino acid did, because I thought, oh my God, like what if people ask me about this? And then like in hindsight, like that is stupid, because how would they ask me about this? Because I don't even know about this.
Right.
So in hindsight, that was just like super weird. Why would I do that?
Would you say that, did you ever focus on like trying to get these rewards? Like, was that ever a mindset of yours? Like, ooh, if I do this, I'll get into the graces of the scientific community? Or was it just simply because you were so driven towards getting this structure and seeing the product?
I was actually never driven by awards. Awards are great and wonderful, and when they happen, but they're kind of arbitrary also, because you rely on your colleagues to put you forward, and it's a lot of work. So it is a little bit of arbitrary, and so I take them or not, and I cheer for my colleagues who get them or not. You know what I mean? This is just one of those things that's superficial. But having said that, the only thing that we have that's worth anything in my job is my reputation as a scientist. And so I want what I do. I want it to matter. I want it to influence maybe how we view the world just a teeny bit. So that's a driving force, and that structure definitely did that. So when you're younger, that's kind of, you want to impress the big guys. Of course, you want to impress all the 100-pound, 800-pound gorillas in the field, and you want to show them, especially as a woman, that you can do this stuff, and you are somebody to be reckoned with. As I get older, and actually all along, I just always viewed teaching and my and training students and training the next generation of scientists as my more important legacy, because that's kind of the gift that keeps on giving, right? I train my grad students, and I instill in them my standards of science and my passion for science, and then they go out and they do the same thing, and it gets amplified. So that's really super cool. And so I've had some really good folks join the lab and leave the lab and do exactly that. So that's really rewarding.
That was actually like my last question that I wanted to ask you on. What would you say is a thing you can give to students that you've seen like struggle through your courses or succeed through your courses? What is the one takeaway where you're like, do this, it'll probably help a lot, or I think this is more beneficial? Anything along those lines?
So this may sound weird coming from me, but maybe not. I really think one shouldn't take this too seriously. And you may get that from my lecture. It's life only happens once. Doing science is one aspect of life. There's many other facets to it, and you should be balanced. And what I actually am fond of telling my students and students, like you, who I think are overachievers, and you always want to do your best. And I tell them, it's a triathlon. It's not 100-yard sprint. You have to pace yourself, and you have to find a way to kind of recharge and recover from the inevitable failures.
Now, I'm sure a lot of us can relate with the topic of work-life balance. It's easy to be swept up with the comparisons and the unhealthy expectations we set for ourselves, but just know you are not alone. We all need to just learn how to chill a bit and remember that personal care is a good thing and not a sign of weakness. And I really appreciate how, despite the fact that a lot of college students may feel like they are really struggling with being tardy or being diligent or putting in their homework on time, Dr. Luger completely ignores all of that and just says, hey people, let's chill out. It's gonna be okay.
And you have to recover from the inevitable burnout. So that is important. What I also think is extremely important, and that's something I live by, is, science had this reputation of being kind of cutthroat and, competition, and you have to play close to your chest, and you can't talk to anybody because they might scoop you on your project. So I think it's gotten a little bit better, but I've never liked that at all. It stresses me out. It's a waste of time. It's like, imagine you're doing your graduate project and you get scooped by somebody, and then it's just a huge waste and disappointment. And so I've always played with open cards, and I try to, like when I think I'm in competition with somebody, I try to, I talk to them and say like, hey, like you're doing this, and maybe we can do this, and maybe we can synergize and work together. And so that's also a message that I'm trying to impart on the next generation, is that it doesn't have to be this horrible cutthroat dog-eat-dog kind of world, but it is actually a team sport, and with a little bit of competition thrown in. Of course, there's always that, but that should not be your driving force. You should not be motivated by like, oh, I'm gonna like totally whip this other person's butt
Right.
because I'm gonna beat them and publish my paper first. To me, that's just horrible. I don't like doing it, and I don't like having it done to me.
I think the one reason why I wanted to pursue science is because I had this image of like, oh, it's not going to be politically driven. But then as you get further into the scientific field, you're like, nope, wherever there's people, there's politics. And it's just like, ugh.
Well, I think that's kind of the literal meaning of politics, is something with people together, right? So I think like if you look up the Greek meaning for politics, that's where it comes from. So people are people always, and science kind of selects for people who can be a little socially awkward, and that's just because we tend to be very analytical and a little OCD, and like what normal person would live this life, right? Carry around little tubes day after day. That's just insane. Right. So it just having a conscious effort. I actually think that holds true for all places in life, is treat people the way you want to be treated. So I really don't like to be lied to or being deceived. And so I will never do that to anybody else in science, because it's just, and it's been done to me, and it just leaves a really bad taste. Yeah.
Well, thank you so much, Professor
this
Luger,
was
for
fun.
your time. And I still remember the fact that you said Tim was the perfect enzyme.
Yeah, it is.
And I was just like, I'm the
Diffusion
perfect
control.
enzyme.
You are the perfect enzyme.
And my friends were like, oh, dude, shut up. And I'm like,
You're such a
I'm
nerd.
sorry.
In conclusion, we learned about the amazingness of the liver, the eagerness of learning the unexplored, cryogenic electron microscopy, insights on failure and success, and not being too affected by either, chilling out, not stressing, the pursuit of trying to make science and research less occupied on competition and more focused on just pushing the science forward. We learned that Tim is the perfect enzyme, and we did all of that while also getting to hear a neat little tune called Selfless Liver. Talking about tunes, thanks for tuning in. If you enjoyed the podcast, hit the like button, comment, subscribe, rate. It really helps. If you didn't enjoy the podcast or you just feel like some constructive feedback is warranted, please also comment below. I'll most likely be able to read all of them because honestly, who the heck is going to listen to this and comment? I feel like the probability very unlikely. Anyway, this is the Asclepius podcast with your host, Blipathy Fu. The next episode will go over the interesting aspects of tutoring for the MCATs and developing curriculum for the MCATs. Peace. Oh my gosh, it's so